coming Wednesday. By that time, you can go through this and then make sure that some problem can be worked out. So this exercise has been given here now. I'll give some hints for this, and later on we'll go to the learning the additional Mathematica codes. Okay, with the exercises, other exercises that I have planned. Okay, to start with, it's an interesting problem or an exercise. In the plane polar coordinates are 5. Orbits around the sun follow the path. This is the r of phi is equal to r0 by 1 plus of epsilon cos phi. So one asteroid follows the path with r0 equal to 15, epsilon equal to 1 by 8, and the second asteroid follows the path r0 is 14 and epsilon equal to 1 by 4. Find the position at which the two paths intersects. Okay, similar to our train problem, na? Right? Parallel train, they meet somewhere. Similarly, here there are two asteroids follow two different paths, but they meet somewhere. Okay, find the position at which the two paths intersects. So, which means R5 seems to be some common point that are going to meet. So, some suggestions is also given for this. Use this exercise to explore some slightly advanced features of Mathematica. Solve the exercise then generally by finding the angle or angles pi at which two orbits R1 of pi, R2 pi intersect. Express pi1 R1 of pi and R2 pi in terms of two scale parameters A1, A2 and eccentricities epsilon 1 and epsilon 2. Okay, you will find a conditional expression that stems from the fact that pi can be multi-valued by adding a multiple values of 2 pi. Experiment with the normal, the solve and put a normal and replacement by a slash dot and a part to extract a single nominally positive expression for the intersection of angle. Then finally intersect numerical value, finally then numerical values. The numbers I gave you seems peculiar, but the answer turns out to be simple angle. So what you have to do, you can think about this problem. It is a polar coordinates. How do you plot this function now? When you have a polar quantities. So you have to take r phi of cos theta, r phi of sin theta, plot as a parametric plot one against the other. Am I right? You have to do that or not? Because it's a polar coordinates, r is given. So we have to take the cos pi of r pi. This means r0 1 plus epsilon cos pi into cos pi, and then r0 1 plus epsilon cos pi into sin pi. Plot one against the other. It's a polar, it's a parametric plot. See, I have just plotted here for you. I'm not going to solve the problem, but I'm giving you the hints what we do here. I'm multiplying this cos pi and sin pi of the same value and plotting as a parametric plot one against the other. It is multiplied by cos pi, it's the real part of it, and this is going to be an imaginary part of that. That's what the function looks like. This is the parametric form. Okay, sine component and cosine component. If you make a plot of that, that is going to be a circle, but it is getting shifted by this factor because of the eccentricity and the R0. Are you able to see that? Sin
yes,
pi?
sir. Yes, sir.
So I made it as a plot, right? Similarly, you have another one. Same function, but change the eccentricity and R0. Cos pi, sin pi. Last one against the other. And if you put them together, they will be crossing somewhere. You can see here, here and here. They're crossing. So which means you have to find out this position. R and pi you need to find by solving this equation. Okay, this is what your task. But I will leave it to you. Think and then solve. And then we'll see if you are not able to do it, we will work it out in the next session sometime. Okay, so it's clear now what is to be done. I hope that things are clear to you people.
Yes, sir.
Taking this problem, it should be solved. And we have to find out a way to get this point and this point because we know the mathematics is required for that. Solve it. One more thing you can do it now. This is a parametric plot, which is a polar quantity. If you make a polar graph, which means polar plot, this and this both 0 to 2 pi, I am already getting both together. I don't have to struggle like this, which means I'm introducing a new Mathematica code for plotting. This is a polar plot. Okay. Hello, this we have not exposed so far. We have been using this parametric plot and plots. Now this is a polar plot. Directly you can take this function and the other function. Now you can see this and this are the same. Okay. They're exactly the same. This is a
Polar plot by directly
polar plot means
both.
You have like you have an xy coordinates, no?
Yeah.
Here your radius is fixed by this
R and theta.
R and then theta is there. Theta is pi, which is varying 0 to pi to make one circle one time it goes round. So you can see the polar parametric plots are actually considered here by taking the polar plots.
Sir, that is instead of theta, it must be 0 to 2 pi.
Where is it?
Phi is equal to 0 to 2 pi. That is 0.
That's 0.
Ah, okay. Here I am seeing like theta.
No. There is a difference between theta and phi. That also you can note down here. You see, this is theta. This cross line across that elliptic shape. This is a cross line. This is slanting.
Yeah, that is parallel. The other one
is parallel. That is what difference that you should remember. This is the slanting line. It is a 0. If it is a line which is horizontal, then it is a theta. And pi is also, you can see, passing through. This is, of course, by look at it, by very look at it, you can differentiate it. Whereas this will be a bit more carefully you have to handle it. Okay. So if I make it as a theta, it's going to be variable. But here it is a 0 to 2 pi 1 circle. That one orbit just completes. Okay. If I repeat it by number of times, you can write it as n number of times. That will be going around on the same path again. For example, if I make it 12, but the line has become a little thick. Going back again and again on the same thing. Okay, nothing new here. Hello? Suppose if I put minus 2 pi to plus 2 pi, what will happen? You get same thing? You're getting same thing, no? That doesn't matter. Okay, so parametric plot. Suppose minus 2 pi to 0 if I make it, I'm getting the same thing. Okay, because this phi will be follows similar thing, starting from minus 2 pi to 0. So we will always try to complete by one round by taking this 0 to pi. Okay, so that doesn't matter. But please remember that this is the meeting point. And what do you do to solve this? I don't have to tell you that you can think about it and get this place where do they meet. There are two possible routes are there, then find out where they meet. Of course, multiple routes are possible because it's a periodic function, repeats again and again. So that's what he is trying to describe here. 2 pi times adding multiples of 2 pi, that also will be available, but put a normal and then take a part of it and then simplify that, you will get the solution what you need. Okay, that can be found. I don't want to do that, so that you just make an effort. Okay, exercise 2. Is it clear for you, all of them, this problem? So what is interesting that we have introduced a polar plot. Okay, let me try to see what is a polar plot. What are the things that one can do with this polar plot? See what is happening?
Spelling mistake.
Spelling mistake. Polar. Now you can go to the polar plots that are given and then try to have some idea. See, polar plot, sine of 3 theta. This is r equal to 1 unit. So r is 1 unit, then this 3t. Actually, 3 loops that are there because of 3t, because 0 to 5 is there. That has been. This is beautiful now. You can see electron which is going around the orbit. Okay, this is the oscillation that you have. And see, polar plot makes it possible for us to visualize that electron is going around in a sinusoidal way. How does it possible? See, polar plot 1 comma 1 plus 1 means polar plot will be this blue one. Okay, let's see. Polar plot of 1 implies, let me take some variable which is varying from 0 to 5. Let me try here. This is what you circle. Okay. 1 unit of a radius is going around as a variable t or as a theta. Anything you like, you can add. It's not a problem. I'll take it as a theta instead of. This is what the result that we have. Then another one is 1 plus 1 by 10 of the sine theta, which means, what does it mean? This amplitude is reduced by 1/10 of that. That is why this is sitting on this. I think you understand what I'm trying to say. This is 1 plus of 1 by 10th of this amplitude into sine 10 such waves that you have. Okay, 10 times, because 0 to 2 pi that has been taken. Suppose if I add 20, you can see the 20 such simple waves that are there around. Okay, this is what our hydrogen atom model, that electron will, okay, sinusoidal or a sine or a sine, but the full wave should be available on that. There should not be any discontinuity between the waves. This is what the idea that's being used here, and you can see here. And if you want to reduce the amplitude further, instead of 10, you make it as 20, get it further. Right? I can go to the next orbit. How do I do it? Any idea? Can I draw this next orbit?
Yeah, divide by 2.
Before that, when something should be done. Divide by 2, no?
Yeah.
Right? So let me try here. Another plot that should be added here 2. Okay. See here, but I don't have the circle. So if I want to have a circle on that, what was I supposed to do? I add a 2 here and make it. I have another orbit here. Now it is this size of that can be increased by reducing it. The amplitudes, probably amplitude one can be reduced, but number of seconds can be retained. Correct? Okay, I reduce the amplitude so that it can be seen, because it's far away. This is 1, this is 2, therefore it will be too small the amplitude when you are going away, because this amplitude becomes too small. To make it 1 by 5, it will be still bigger, you can see. This is how things can be generated further. So you can optimize it by maybe take 10 of itself and then look at things. Okay, if you wanted to have another one, just put a number n and then do the manipulation. You can have a n number of such orbits that you can have. So this is one of the another polar plots, and then polar plots with other options, plot styles. You can differentiate one from the other. This is oscillated thing by using a dash. Use the green color in the directive. But the other one is dash line, thick. This is the thick one. Make orange color. Okay. Then there is a scope for the sampling is available. See? Beautiful pictures that can be generated with this polar plot of 10. How does it look like? And this is the 2 square root of sine to 2 pi. And then this flooring, with the step by step you can go. That's what this floor means. And you can make again flooring structure like maximum recursion. This is another way of generating a kind of a picture. And then you can have other things. This is sine 2 theta. Call out means I think it will be want to know what is call out. Any idea? Yeah, I don't know what it is, but I can find out. That's how this advantage with this. I've really not seen that. I read some time back in Mathematica, but I don't remember that. So I just want to know what is call out. Okay, I can find out this. What call out is the data, display this in the plot, call out, point to data. What is this? Maybe what time will read it. Call out data, expression. Display the expression in the plot as a call out pointing to data. Okay. Get the idea? I'll remove this. See what is the effect of that. Let me find it. You know what has happened? What has happened?
Same plot.
Same plot there, but call out gives, this is, if I make a call out, C-A-L-L-O-U-T, call out, call out, then that will be closed because it's a statement. This name of the thing that's going to be added here. You can see this sine 2t is added here. This data what you have generated is nothing but your sine 2 theta. That's what it says. That's what the meaning here is. Call out data expression. Display the expression in a plot as a call out pointing to data. That is what the meaning of this. If I remove the call out, I will see only the plot. But if I make a call out with this, this indicates this is what your sine 2 theta is your data that is being plotted. That's what it indicates. Okay. I remove this one more time. Check out. Let's disappear. So if I add call out, that will be entering. There are other options for the call out again. Positions can also be given. Okay, display call out anchored at a position specified by APOS. So that's also possible. You can see now you can call out label, it is fixed here. Okay, so call out, there are other things that are also given in terms of writing the data point, like 5 by 4 and 5 by 3 pi by 4 like this. So this is other information that you have. This is the polar plot, sin t, cos t, plot labels are there by sin and cos. Well, wow, that's great. You can see this plot now. Sin and cos polar plot, they differ by an angle of 90 degrees. Therefore, the circle one sits here and another one sits here. This is cos and this is sin. Great. Get the point? I hope you are able to follow this polar plot. Cos of t is this one. Okay. Sin of t is the other one. And here it is the all out square root of t. It is almost growing. This is given some additional information, label and other things there. Label size is given. Like this, there are other options that are a presentation. Now we can see here polar plot 1, 2, 3. 1, 2, 3. Nice. We have seen. Then we can have another options. Sin 4 theta. This is what your sin 4 theta. Of course, then other things are also given and the color options. Other things can be explored. Here also background has been changed. So there are 59 options that are available for a polar plot. Then there are some applications. Okay. There are some interesting applications that may be useful to you also. And this is another interesting special plots are there, properties and relations. And then you have the contour plots along with this maybe accompanying, I don't know, yeah, region plot, contour plot. Implicit curves in the region. Spherical plot 3D. Okay, plot additional things which are not interested immediately. But you can see the number of options that are available under the polar plots. So this will be definitely useful at later stage for us whenever we have a polar complex. Okay. So I hope this is clear now. Connected to these activities, I will leave it polar parts of the area. You can take it now. Okay, this problem, as I said, basketball is launched from a mid-court at a 30-degree angle with a horizontal and at a height of 2 meters toward the basket, 12.5 meters away. This is the distance. Height is 2 meters toward the 12.5 meters away. If the rim is 3 meters above the floor, neglecting air resistance, what must be the initial speed of the ball in order to sink the basket? Which means what should be the speed with which it should be pushed out with an angle of 30 degrees so that it can go and fall in the basket. So this is easy problem. You just set the equation for a V from these numbers that are given, and rim is how far it's there, and 2 meter height in which you are starting, and then this is what the distance is given, range is given, the angle is given. Set this equation, solve it, and find out what is the V0, the velocity that's required so that it, in order to sink with the basket. This is also easy problem which you can work it out, because already we have done enough on this so-called the projectile motion. Next is another interesting problem. Now, the figure below shows a resistor R, inductor L, and a capacitor C connected in parallel. You can see 3 of them are connected in parallel. An AC potential difference of V of t is equal to V0 cos omega t, which is equal to real part of I omega is applied across the open terminals. Okay, with this we're going to connect an AC. This is what we connect. Yes. Whether okay, in this case, the concept of resistance for DC circuits can be replaced by impedance for AC circuits. If all of them are resistors, then it will be different. Since you have a capacitor and inductor, we are instead of calling it as a resistance, we call it as a inductors. The resistive part is Z of R equal to R. Inductive impedance is Z, L, which is equal to I omega L. Capacitance is ZC equal to 1 by I omega C. Okay. Now, Zs can be used as resistances using the same rules for a DC circuit, which means 3 resistors or 2 resistors. Yeah, 3 resistors in parallel. How do you find out the effective resistance? You know the rule. The effective value of resistance when they are parallel, what is the rule? 1 by R effective equal to 1 by R1 plus 1 by R2 plus 1 by R3. Replace that R's by this ZC and ZR and ZL. That's all. That's what you have to do. That's what the information is giving. If it is a DC, effective resistance is 1 by R. It's here. 1 by I omega C. Because ZC is the resistance. 1 by R ZC is 1 by I omega C. Then you have the ZL, this reactance, I omega L, which is again like a resistance. So 1 by ZL, that I omega L should be taken. So we have a complex quantity here now. Okay, the Zs can be used as a resistance using the same rule as DC circuits, but the complex itself has both a magnitude and a phase as defined by the absolute value, APS in Mathematica, and the phase argument, ARG. Okay. Find an expression for the impedance Z of an above circuit segment in terms of R, L, and C, and the frequency omega. Using the realistic circuit values, for example, 1 kilo ohms. Okay, please note 1 kilo ohms, which means 1 into 10 power 3 ohm, 1 kilo. C is 100 C microfarad. So don't miss this one, otherwise you'll have a wrong result. 100 microfarad, which means 100 picofarad. Hello? You are able to understand.
100 PF.
100 PF, because there's a micro and micro, 100 PF. So if you miss this, then you have a wrong result. And L is equal to 5 millihenry. Plot the magnitude and phase as Z as a function of omega. Plot the magnitude and phase of Z as a function of omega. So you have to find the magnitude and phase, then make sure that you are finding as a function of omega. It is best to make a plot using a log scale for omega. See the function log linear plot. Now we are going to learn a new one, which I'll give some typical examples right now, which will do this for you. Okay, log linear plot, which means we already learned here polar plot. Now there is another thing which is coming, which is new thing which you are going to learn now, which is a log linear plot, which will do this for you. Now, solve for the value of omega at which the phase passes through 0. You might encounter difficulty using solve depending on how you determine the phase because of the way Mathematica treats the complex numbers. However, using refine with the assumption that R, L, C and omega are all real and positive, combined with RE, real part and imaginary part and the complex exponent, you can end up with a brute force version of the phase that will work with you solve. So he has given some of the hints what is going to happen when you start using it and handle them, taking care of all this refine and real, imaginary and complex exponent. All this can be done. So this problem really makes you to learn additional things like log linear plot. You can make a plot of real part, you can make a plot of imaginary part, you can make a magnitude of this total impedance, and then phase can also be calculated and it can be plotted. All that is possible by this exercise. Okay, so it's better to learn, spend your time, and we will see how comfortable with this Mathematica when compared to the other languages when you work. Okay, so I'll give some input for you to, for example, I'll take one R and a C. Or I can take R and a L, and you add this third one and then do it. Okay, I just indicate now how do we solve those problems when you have a two components are there. You add the third component to do the same problem. Nothing great here. And first exercise, what I would suggest you is that, you know, R and C. What do you get R and C? Students should be in a position to answer now. What is, if you multiply R and C, what physical quantity you will get it? No? What do you get? Anybody to answer? What physical quantity that you would get when I multiply R and C? No. RC is in an RC circuit. What is this RC?
Omega frequency.
Yeah. Omega is frequency. That's not interesting. But what I'm asking, multiply this R and C. What do you get? Okay. You remember that L by R or R by L?
Time constant.
Oh, that's right. R and C will be a time constant. There is another time constant will be there along with the L and C can also be used for to find a time constant. R by L also can be used for finding a time constant. R and C can also give a time constant. If I use L and C alone, it is going to be an oscillatory circuit. Okay, energy will be stored, dissipated, storing, dissipating, storing, decaying, storing, decaying, stores, decay, stores, decay. L and C if I have. If I have a R and C with the DC component, DC if I put instead of an AC, there's going to be a decay. And how fast and how slow that's going to decay depends on the magnitude of R and C. The rate at which they're going to decay will be decided by the product of R and C. or it is going to charge a capacitor or discharge a capacitor. Here it is not charging or discharging, because it's a AC which is given. Okay, so therefore it will be get charged and discharged. How fast you are going to charge it, how slow you are going to charge it, that will be decided by the R and C, and that is given time constant. The time constant which is responsible for the slow and fast rate with which the capacitor going to be charging or discharging. Okay, if it is a millisecond, okay, or see if it is a millisecond, how do I select the for a millisecond values? 1 kilo ohms. C must be, what should be the C value? I have selected 1 kilo ohms. Time constant I want to have a 1 millisecond. How much should be the C value? So now you can see that you realize how much. Simple calculation now. I know RC, R I know, C I know. That's equal to time constant, which is, what is that? What did I say? 10 power minus 3 seconds. Okay, minus 3 seconds. This is the equation, and R is how much? You see, this even for this calculation I will use a Mathematica. R is 10 power, how much? 10 power 3. I wanted to solve this equation for what? This is an equation which you have said. This equation is right for, but what are mentioning here? I said 1 kilo I am using it. Time constant I want to have a 10 power minus 3. Then what should be the value of C? So solve for C. So maybe I will use small c, because C is already being used by Mathematica for other purposes. Okay. So what do I get? Now it's going to be 10 power minus 6. And you get the numerical value of that by putting n. So it's going to be 1 microfarad now. Now, I have a time constant now. Resistance is 1 kilo. Much is the 1 kilo, which means 10 power 3. Then this is 100 microfarad. What does it mean? That's equal to 10 power minus 6. 1 micro, or another micro is 10 power minus 6. If I multiply these two, that is equal to my time constant for this. I have not introduced any decimal anywhere, therefore it gives an integer form. Therefore, I would like to put it a numerical form. How much? It's going to be 10 power minus 7 second. Understand? This is the time constant that you have for this R and C. What is the value of L? 5 microhenry. Okay. Now I have another question. L by R by L. What is your time constant? L by R or R by L. What is your time constant? Is it L by R or R by L? No idea?
L by R.
L by R. Sure, huh? Very good. Let me try here. So 5 microhenry. Micro or milli? So milli, M is given. My 5 into 10 power, how much? 10 power minus 3. Divided by L by R, that's what your time constant, is it not? 10 power 3. Okay? You know, I'll put a decimal here, 0.0, so that the answer will be automatically, I will get it as a time constant here. So there is another time constant which is how much? 10 power minus, which means 5 microsecond is one time constant. And I have another time constant which is 10 power minus 7 seconds. Define two time constants. There is one more time constant, L and C, which give a frequency. What is that time constant? What is the time constant? L and C is given. What is the time constant will get you? What is the frequency of oscillator when you have an LC is given? 1 by
LC.
square root of 2 pi
Okay.
square root of LC into 2 pi, is it not? Okay, then in that case, I'll just take 2 pi inverse of that is going to be times square root of L, and the C value is so much. L is already given as so much. 5 millihenry, 10 power minus 3. That's good. And then C value is, LC, how much? LC is 100 microfarad. Sorry, 100 microfarad. So which means I'll put again 100, 10 power minus 6, and again 10 power minus 6. This is going to be another time constant, which I would like to convert in the form of integers or the decimal. This is for this. So now you find there are 3 time constants that are available. And if you do analysis of this with the frequency, this information must be available for you with this components of R 1 kilo ohm, C 100 microfarad, and L is equal to 5 millihenry. I will explain to you one of them. For example, this is R and C, time constant is 10 power minus 7. If I make a measurement of a frequency analysis, I should get this information from the, suppose inductance I don't have. I have an R and C. The circuit, assume that inductance equal to 0. I have an R and C which is parallel. If I do this analysis, I have to follow the rule, whatever he has given it. What is the rule says? Just 1 minute, I'll just show you the effective resistance. What is that he is saying? 1 by of R effective equal to, sorry, this is the 1 by, what is the first one is R itself, is it not? ZC, ZR equal to R plus, what is the other resistance? When you use C alone, B equal to 0. Let's take this, ZC is the resistance. 1 by R, 1 by 1 divided by 1 divided by, I should be type double stroke. This is a complex quantity, square root of minus 1. Double stroke of I, escape. I just repeat again, escape. Double stroke for I, and then press it. This is equivalent to your complex quantity I. Then what do you have? Omega and T. Is it right? What I have written is right? Because this is what your resistance here, no? This is in a reactive part. See, that is 1 by of, this is the resistance line. 1 by of, 1 by is the effective value because they are in parallel. I have removed this one. Inductance I don't want. I just retain this C alone. Okay. Later on you can add. If how do you do that one? Just plus, what do you do? Add I omega L. That's all. Get the point? Or effective, if I include that, I omega L, if I add, then all the 3 has been taken into consideration. Let us try to do this first 2 and then see the third one, which you can make an effort. Right? Any issues here? No issue, no, so far. Fine.
No, sir.
Okay, now we will see this. This is what the result that you have. If I inverse both the sides, these are golden rules in mathematics. What are the golden rules? What you do on the left hand side, do it on the right hand side, nothing will happen to your equation. I have taken inverse of this, inverse of this. What is the inverse of that? RE equal to 1 divided by inverse of that is going to be I. No, omega. Where does it? Where has it gone? Where it's gone? Where it is defined somewhere? No, they are not defined anywhere. No? Where is this fellow omega? What the hell is happening now? Why should it this missing? Which means somewhere I have defined omega already. Okay, so what do? I have to do something here. You know what is that happening now? Omega is already defined somewhere, which because already 197 input outputs already there. Somewhere I may define and forgotten. So that's why it's taken as that number I have used it. That number happens to be 1 and it's not appearing here. So if you wanted to have it again, I have to redo the things starting from here, probably starting from here, so that there will not be any issue in terms of defining these variables. Please note that you follow 197 output. So much I have done. So to get rid of this thing, what we can do, go to the evaluation, as I said, quit kernel local. I am leaving from this kernel, but I am within this notebook. See, all it is being removed. Now it is fresh. The whole thing has become fresh. I'll start from here. If I want to come back, I can come back there also. Okay? You follow? Now you see. I'm entering. This will be the first input, and that's the output. Omega is here. I'm able to see the omega. I'm going to take an inverse of this both. The inverse of this is this one. Re is effective. That's going to be your effective, which is an impedance here, 1 by E of. Agree with me? Is there any mistake has done? Because I'm reversing this left hand side, the whole thing's also reversed here also. Is it not? Am I right?
Yes, sir.
Please do note down. Otherwise, you'll have a problem. Okay, now I can take the right hand side, which is R effective, which is an impedance, probably total impedance, because it is combination of a resistor and a capacitance. So this is going to be an impedance for me. This Re effective value, R effective is nothing but your impedance value. So this impedance has a real part and imaginary part. So I can take out this, copy, and then put it over here. Then you can probably simplify this and see what's happening. First level, no. Otherwise, put them together. See, together also giving a I, and it's a bit confusing. Therefore, you just take it as it is. This is the total value because you don't know what is this result, but it's not an issue at all. Multiply numerator and denominator by I and I. Minus I. Now, I want to get this back. So what you do is just you remove this one, doesn't matter for me. I'll retain this as it is. Then I'm going to find out what is the complex quantity now. I want to expand this. Find out what is the real part of this. Then I have only R and C, which is parallel. This is the real part. Okay? Copy. And I want to have an imaginary part. Put them in a list so that they will be on a list, and you make this as an imaginary part. This is the complex expand thing which we have learned, and close it. Look at that, whether this is coming properly or not. The real part and imaginary part, complex expand. You know what is the mistake? Huh?
Expand the spelling is
when you're wrong, you spell, and this is still as a blue. It's not become black. EXPAND. Now it has become black. Okay. Now we are getting it as a real part and imaginary part. You just have to simplify. Let's see simplification. How does it look like? Okay, this is one of them is real part, and other one is the imaginary part. Okay, so you can see there is a minus sign here. Well, how it has been done? It has taken a complex conjugate of numerator and denominator, and we take a complex conjugate of this, multiply, divide the denominator and numerator by that complex conjugate, and simplify. All has been done, and it has been given this result. That is why you have a minus sign. Okay, so if you ask to simplify, full simplification will give this numerator. Okay, that doesn't matter now. Whether simplified, same thing you are getting it now. That doesn't matter. You wanted to put r square also in the denominator, you have to do some simple tricks. Maybe together we try together is the result. I'm putting the whole thing together because I don't want to see this 1 by r separately. So now I have the real part and the imaginary part. This is what the result is. If I add 1 plus of 1 by I omega L, inductance also has been considered. Okay, it will be easy that you do it. Okay, what do? I just simply add here as 1 plus 1 by I omega L. Please note, I am not adding here directly because it has come from the inverse component. So therefore, when you add here, you should be careful. Otherwise, you have to add it here itself. Okay, this is fine now. I hope it's clear. Now, if I plot this is an impedance. That's what you ask him to plot. You can take a ABS value, or you can plot it, or independently you can plot it, and whatever you like, you can do it. But one thing is, you have to make a log linear plot. Then only it looks good. Because you have to cover a wide range of the frequency. Your time constant is how much now? 10 power minus 7 seconds. So your frequency should go beyond 10 power minus 7. I'm sorry, 10 power plus 7. Then only the spectrum will have the information. So what do I do now? I'll just take this log. What is the plot says? Log linear. Log linear plot, yes. It's asking for a log linear. L-I-N-E-A-R. Log linear plot. Close this. So, what are the values of R now? R is how much? R is 10 power 3. Because 10 power 3 now. 10 power 3. Okay. Next. If you want, you can define outside the R equal to. It's also not a problem. C. What is the C? Capital C or small c? Small c is how much? 10 power 100 microfarad. So how much we have got it after multiplying that? 100 microfarad, 10 power minus. I'm sorry, that time constant is how much? 10 power RC 10 power minus 7. This is C value is how much? 10 power 12, and it must be 10 power minus 10. Am I right? Minus 10. That's the capacitance value. Okay, now what could be the value of this omega now? Can you guess what is the value of omega should be? Go to a range of, say, somewhere about 10 power 4 or 10 power 3. That's what you are. Let me take from 10 power 3 I will take. That's 2, 10 power, I'll go to 10. How much is the order? 7 orders I covered. Keeping in mind that I have the time constant is RC is 10 power minus 8. This is 10 power minus 10 power 3 or 2. That's 1 kilo. Okay. Okay, let me make a plot now. This is okay. And why do you make such a wide scale? Because my time constant is 10 to the minus 1 unless you see, for example, let me try here. I'll take 10 to the power 5 and make a plot. Let me see. Ooh, what is this? Is this straight line? Does it make sense? R is available, C is also available. Anything is not been given. No? Now information started coming down, no? Small chit. Now if I go to 10 power 10, then you would see something interesting. That is the result. Exactly at 10 power minus 7 is the time constant at which you see that at the frequency of 10 power 7, there is going to be a peak. And what do I do? Instead of taking a minus, I'll remove this by multiplying a minus sign, which means the graph can be, this negative sign can be shifted up by multiplying by a minus sign, which implies that I'm just removing this sign. And you can see this is what the result which we are interested in. This has a lot of information. This is what your impedance spectroscopy results. You can see there is a spectroscopy, there is a resonance around this. When time constant is equal to 10 power frequency, the 10 power 7, and you have a time constant information, they are meeting at this point. Real part is this, and this is an imaginary part. Okay, you can see this is such a useful tool for us to get the time constant. Once you know the time constant, I know the resistance part. When R equal to 0, this is 10 power 3. When omega equal to 0, 10 power 3 is the resistance. I know the time constant, which is 10 power minus 7, because I know the frequency at which the maximum is reached. And once I know the resistance and time constant, capacitance can be found. Even if I don't know this information, by looking at the spectrum, I can get the information about this, time constant also available for me. See, this is the most powerful tool to analyze this impedance. You'll get this information. Now you can think, add that, and complete the exercise. And you can think about what happened to the other time constant when you have a inductance. When you add, I sent, there is a one more time constant is there, no? Then L by R is 1, and then you have a L and C, another R by L and or L by R, and then LC also available. Those information also must be reflected in your frequency difference spectrum. And you can see this is your scale, which is log, which means when I start from 10 power 1, no information is available here. Okay, because the magnitude is same. Real part alone is reflected. So your frequency response started showing the magnitude of value, higher value. It started increasing around this and then goes down. And you can really spend your time to understand why this is going up, where it will reach maximum, and how this is coming down. Right? This is the function that has all the features. Okay. And in this now, log linear plot, I just change. See how I'm going to do now. Manipulate. Okay. I just take out this resistance, or I'll change the capacitance instead of a resistance, or I can change both. Okay. I'll take plotting. So my R value, the initial value what has been given is 10 power 3. This is R. I go up to, let me take 10 power 7. Up to 10 power 7, I'm going to change. So the problem is, see, now capacitance, see, starting from, how much is this magnitude now? 10 power, and constant is 10 power 7. So capacitance, what has been given is 100 into 10 power, so 10 power 10. I'll take 10 power somewhere about minus 7 to see 10 power minus 9. 2 orders of capacitance value. I change it and then close it. It's manipulated now. See, now what is happening in this time constant will be RC 10 power, how much? 10 power minus 3, no, 10 power minus 4. So which means this peak will go to 4. And see, when you start entering, the peak will be shifted to 10 power 4. 1. Yes. See? Just come here. Now if I change the R value or a C value, you can see this shift here. Okay? This is the beauty of this. And change the R value, magnitude goes up and time constant also shifts. Smaller than that also is possible. So this is what your time constant. I didn't go to 10 power minus 10 power 7 at all, which means I can go up to 2 orders further, or 3 orders further. Then I can go up to, when I change the C, R is not changing, only time constant getting shifted up. Okay? Follow? And this is the magnitude change. Plot range this. Your magnitude of resistance become too high and correspondingly your time constant changes. You can see the shifting can be seen. So this is the combinations of R and C with the different possible values of capacitance and the resistance. That information is available when you make a measurement. This is a fantastic measurement and it's a nice project for people to work on. Take a magnitude of resistance and a particular value of C and measure it by using LCZ meter and make a plot and compare the plot with this equation. It should go very well with your measured data. RC parallel. Do a soldering of resistance and capacitance in parallel. And if you have LCZ meter, take the data, plot the data, and use this function, plot them. You would see this nice result. And you can imagine that when you have a inductance also, put this again, do that, find out this kind of a behavior, and do the wonderful analysis. So now, if you want to have a ABS plot, what you have to do, just take a ABS of this imaginary complex quantity and then make a plot. What about the phase? What about the phase? And this is what your phase. I'm just showing you the phase. Imaginary part divided by real part. That is what your imaginary divided by real part. Minus CR omega. That is your tan phi. And inverse of that is going to be your phi magnitude. So we know the ABS value and the phi, and it can be plotted and it can be shown. So you make efforts for different values and then check whether they are falling in place, and you can always confirm your results. So this is what the interesting aspect about this issue of the problem. This is the phases can be given directly like this. This is what your tan, and you take an arc tan of that. That's the fix. That can be plotted. Okay. So completes your, what is the exercise? This must be third exercise, no, second or third exercise. Come to the fourth one. This is rather simple. We have done it. Only thing little additional. An object moves in one dimension according to the x of t. 5 e per minus t square. Find the velocity and acceleration. This is the e per minus t square. Plot these along with the position on a single graph with legends. Add legends. Find the times at which there is no net force on the object. How do you do that? Any guess? How do you perform that? I'll give you a hint alone. You have to do that. Find the time at which there is no net force on the object. Any guess? Come on. If I take a first derivative and second derivative, what do you get? Second derivative of this?
Acceleration.
Acceleration, that's going to be force, right?
Yes.
Multiply with the mass, any unit, but mass, if it get cancelled, doesn't matter. No, you have acceleration which is there. Then that you equal to 0 and solve for the equation. When it's going to be 0 at what time? Okay, find the time at which there is no net force, which means you take a derivative twice equal to 0. Find out at what time that force or acceleration goes to 0. When acceleration 0, force is also 0. Correct? So you find out that. That can be done. Not a difficult thing. Derivative 1, derivative 2. And you are going to plot velocity and acceleration together first. And then you are finding out what time this acceleration goes to 0 from this plot. Next is, an object moves in one dimension according to this equation, x of t. So that this motion results from a force. This is another way to, it is similar to this, isn't it? Only they apply to a particle of a mass m is equal to half, whose initial position and velocity are both 0. Okay, so this is another way to put the problem. Here it is x of t is little different from what you have here. Okay, so you have to take a derivative 1, derivative 2. Then that derivative seems to be of this nature. This is applied to a particle of mass m is equal to half, whose initial position velocity are both 0. What you have to find? According to this, show that the motion results from a force. How do you go back? How do you get this one? This should be proved, no? It just started from here, and you are getting this. Any idea? From here, I have to come back and show that this is what the result, corresponding mass equal to half. Okay. So what do? Integrate twice and reach this result. Then you have the result. Fine. This is dv by dt. Okay, m dv by dt. So r is equal to m x double prime dx square d square x by dt square equal to this. Integrate twice, and this result you should get it, which means that where mass has been taken as half, then this will be the result. That's what you have to show. I hope it's clear for you. Repeat again. You integrate this twice. When you have an integration with the mass equal to half, then this result will be automatic. That is what he is supposed to show. Okay, do that. So these are the 5 exercises. They are very good. I'm sure that you will learn a lot of things. Have patience and use the codes Mathematica, which already has been developed. Spend, think, and then I will spend, think, and then make sure that things will be fine. Okay. Clear? I'll save this and send it to you immediately after the class, and you can use them. So these are working out. So now learn Mathematica code now. Yeah. So there are whatever possible we try to see for another half an hour time. Okay. So let's start with this. We're going to learn part A. Differentiate the following expressions with respect this, and simplify the result. Find this. This is a partial derivative, isn't it? Where f of x comma y equal to this f is given as x square minus 1 sine hy cos x. And this is a partial derivative of dou f by dou y dou x square, which means x derivative x time dou f by dou x has been done twice, and then with respect to y once. Clear? Problem is clear?
Yes, sir.
Clear. So now we start. Do this as an equation 1. D of tan hx. No hyperbolic function tan h. And then sin x divided by x. Little complicated in differentiation, but it will give a result. This is what your result. And any simplification is possible. You can simplify and you can check it whether it simplifies to further. If it is done, okay, otherwise leave it as it is. Okay, let's not worry about putting them all together, different terms of the question. Okay. U by V form. You can cross check it. And that is what the result. You can always cross check this, right, using the U by rule. And equation 1 simplify, of course, he has given it here below. So this is what we have done there. Okay, then alternate notations for this D is this one, which I already mentioned to you. Palettes are there, basics, classroom assistants or basic assignments are there that can be explored here to get the derivatives. You can see here derivatives. That's what being used. And that replaced by this function. You don't have to add anything here. Those suffix and give this function. Our derivative will be taken and simplified. You follow? You can see here. This. I'll put it over here and then simply enter this. And this is being taken over here and put it over here. This is what the expression that you could get it by making a mere substitution. They are one and the same. Okay. Now I'm able to do that. I just take a differentiation of this. That's going to be 0 here. You know why? Because it's supposed to be differentiated with respect to x. If you don't add that, I will not get the result. I'm getting it. Simplify same thing. Add along with that. So whatever which you have found with the D, a function with respect to x, I'm able to get it by though suffix x function immediately should come. Don't put anything, constants are there. When any constant thing is there, take it out and then do it. That's what the result. Next, part B. Well, part B is little involved. You have a partial derivative. X comma y, there is a sin h y cos x plus x square minus 1, which means cos x, x square minus 1 is one of the function which depends on x, and this is the y variable. That's why it's f of x. Okay, now we can see this, what is happening, f of x underscore y underscore, and defining like this because there are two variables are there. Now, I have taken this 3 times. 2 times is x. Okay, that's what the problem says. 2 times the x derivative, 1 time y. See how simple is this? Okay, now if I do that, I'll get the partial derivative. Enter the function. Amazing. You see this. This is what your result. And you see here, d of f of x y, x2 times and y once. Simplify. The same as what you have here. I hope it's clear. X should be done twice. That's why x comma 2, y should be done once. So they are one and the same. So partial derivative, partial differentiation is comfortably handled by using Mathematica. It is not a complex things at all. It's very easy to handle them like this. Okay. I hope this is clear for you now. Please remember this, that it can be added and you can perform this. Right. So this is a part of differentiation in which we have done the only one variable and then 2 variables. You can have multiple variables that can also be handled. Now we have another interesting problem. Now you just see these are all the similar type of differential equations. Okay. 1, 2, 3, 4 differential equations which I have. So now you can see I'm going to list all the 4 equations at a time. Then define it as a equation 1, 2, 3, 4. I have put a bracket 1, 2, 3, 4. D solve y of t, of t, and make a list of that. So which means this says and add, perform this with this. This is the variable, do it and make a list at. listed all of them. That's what it means. So please see that these three are yet to be defined. This is already defined somewhere available. Therefore, I have to make sure that equation 1, this is what your equation should not be clashed with already defined somewhere. So therefore, what do I do? To start with here, I can clear equation 1 or, okay, see, somewhere equation is defined. Yeah, already defined, no? This fellow will come and sit here. But you are going to define it again, therefore, there will not be any problem, hopefully. Let's see. Because this equation is redefined here now, there will not be any problem. And we are making a list of differential equations. Say 1, 2, 3, 4. 1, 2, 3, 4. All the 4 at that time, this can also be solved. One by one also it can be solved. Okay, because its capabilities are too much, with simply similar type of a differential equation, which you have first derivative, second derivative. Simply we are putting all of them together and making a solution to all the differential equation at that time. But there is a similarity. Two different, completely different type of a differential equation you type, there's going to be a problem. So let me just shift, enter, and see the list is being taken and it is being defined with this equation. 1, y prime, dy by dt is y prime, 4yt equal to t square. First equation. Because of this list, and this is another list, this list is equated to this list. Therefore, first one corresponds to the first equation. Second one corresponds to the second equation. Third one corresponds to third. Fourth one corresponds to fourth. That's amazing. I'm looking for the solution. Apply desolve. The solutions follow. And when I am applying, you see this is hash has been used. What the hash means? This hash, the list what is there now, 1, 2, 3, 4, that will be taken at first one will be taken, second one taken, third one taken, fourth one has been taken. For each one of them, find y of t as a function of t. And this and means that repeat it. Yes. Apply this list and repeat at the list. This is the list that you have. So at this list, perform all of them. That is what this and will take care of. You don't have to use any do loop or such system. Simply just make a hash here, and what is that one should be done at the list. At the list one, desolve. This is a powerful tool now. This is a powerful tool. Just such a simple statement which solves the 4 differential equations at that time. Let's check whether it's solved or not. It's been solved. Okay. You have a solution now? First equation, second equation, third equation. Okay. Of course, you have the first order, one constant will be there. Second order means 2 constants will be there. Let us put the result C1 and C2 equal to 1 by 10, which means all the constants are taken as 1 by 10, C1 and C2, for each one of the equations. Solution 2, you just use y of t, the solution substituted, C1, C2 is given. So you will get back this after substitution, 1, 2, 3, 4 differential equations with this constant C1, C2. Plot solution 2. All the 4 at a time. That's only one variable. I'm going to plot it. See? Great. I'm able to see all of them because I am asked to give a plot legends expressions so that I know which color corresponds to which color. This is one of them is here, and the other one is next one, third one is this, and fourth one is this. And all of them are here. Okay. So now we have solved 4 differential equations at a time, provided that there are similarities should be there. Because if they are completely different, then it will have a problem. So similar equations can be put together and it can be solved, and we will get this result. I have all the 4 at a time. So yeah, what is the any difficulty you have anywhere? Only thing you see, list should be handled properly with an understandable form. I have a 4 equations, put it in the list form, 1-to-1 correspondence has been established. Then by desolve is going to be common for all of them. Therefore, at the list is done by using a hash. This hash is taking this list one by one, repeat, and at means you do that desolve at this list. So the result. Then every rule has been used here, solution. And then you are getting the form where it is with this constant has been obtained now, and we made a plot. If you want, you can change the constants now and then make a plot again, or you can have 2 different constants here, or you solve the equation depending on the nature of the equation. You take the values and then make a plot. So you would see this corresponding result. Now I change the constants now. This is what the result, and the plot will be now different. Okay, it's getting modified now. Or I can have you solve them and find out the constants C1 and C2, substitute it back, and then each one of them can be substituted for C1 and C2 and solve them also. That's also possible. I'll make it smaller value, 2, and this I will make it 5 and see what is the consequence of that. So this is what the results that you have, and this equation goes up to PQ. Is it right? Variation up to goes to PQ. Fine. That's the greatness of this. And you can realize now how interesting is this and how comfortably one can vary the parameters and get the results. Okay, now next let's integrate the function. We have done the differentiation. We have seen the differential equations of the similar type. We are coming to the integration. So integrate sin x exponential minus x squared by x from minus infinity to plus infinity. See the range. Find the exact approximate values. The exact and approximate values. 1 by of 1 plus x power n, or n equal to 1, 2, 3, 4. So it's also should be integrated. Okay, so now integrate. X varies from this to this. Find out the number. It's an error. Error function because of e power minus x square. Pi error. And probably if you want to have a numerical value, it can be found. So solution 1 numerical or n integrate sin x. You know sin x by x? You know what is the sin x by x function? We call it as a sinc function. That has fantastic properties now. So now we are using a n integrate, numerically integrate this the double exponential oscillatory. That is what the method. Double exponential oscillatory method. Let's see what's happening to this. Look at the numbers. Which has been done integrating it with an error function. Numerically, I have taken that solution 1 or do numerical integration. Then you get this result, which is one and the same. Only thing, working precision, we have given it as 16 digits. This is the 16 digits accuracy. Okay. This is about 4 or 5 digits, but number, if I copy and paste, you will get the accuracy in a wider range. Because Mathematica gives certain results and that's what they say. When I copy and paste that, I have all of them for the digits. 1.35198. All numbers are there. I just copied and pasted it. It gives only display it only this, but actually internally this much numbers as accuracy has been evaluated. Okay. So how does this function is going to behave? Why this is happening? How does this function? Now you can start analyzing this. When I plot it, sin x by epsilon, what happens? Introduce the multiplication of e power minus x square and see what's happening. And what is the reason for error here? Why it's coming as an error here? Once you have an error, is it possible for me to get the inverse of this function? What does it inverse of the function? Can I do a differentiation of these results to get this one? You know what I'm asking? Integrate it, I'm getting the results. Can I differentiate this and get this result? That's the question which you can ask, because we don't ask such questions. But here, if I have these relations differentiated. Okay. If I take integration of this differential values, I'll get the function back. But do you get it here? Okay. You can think about it. But then what is the problem with the function, such functions? And why should we use such functions when there is you are not in a position to get back that, but still we are using it in our physical problems. What does it mean? This is the thing which one has to think and try to have some more deeper understanding about such function. You know, sinc function. This is the sine x divided by x is a sinc function. Okay. So numerical integration 1 to 10. Tan x integrate. Perform it now. And then probably we can start with this and we can have some questions. This is the result. It takes quite a bit of time to calculate it. Great. Sleep. Yeah, you're getting it back. It's numerically follows. So n integrate gives the result. If I ask to do that n value, it gives the number. Okay? Otherwise, it's simply linking. It doesn't know what to do. But when you ask for integrate this equation x1 to 10 numerically, it gives the number, which is same as n integrate. That's what the result that we have. So it appears that it seems to be even complicated, difficult problems which we deal can be solved comfortably, and that can be handled the way you like it later stage. Okay. So we can have some couple of questions, another 5 minutes, then close down, and we can meet on Wednesday, no? Hello?
Yes, sir. Wednesday, that is what you said, sir.
Huh?
Wednesday.
Wednesday, same time.
Same time, sir.
Same time, because I have to shift and maybe I have to settle down there for a while. Then I will start the classes again. We'll continue. Meantime, you can work out this exercise problem what I have given. And already there are some information which is available for solving the differential equation and the integration differentiation. People start performing that integration differentiation, taking the specific problems which they have studied in mathematical. You have an Afghan book, take out and then start working on that. You take any of the differential equations, just start, define them and then look for the solutions. And there is a methodology that has been given that you try to understand for solving this equation and verify whether this Mathematica gives correct results or not. That can also be tempted now. Similarly, integration also. Take any standard integrals, one by one, you just check it whether this performs the integration or not. If it doesn't do, then you have to look for the methodology, alternate things should be defined. For example, this is method here. Okay, double exponential oscillatory method that is being used because this is not a simple integration. It has an error function here involved, and therefore it should be done very carefully for a usual method. This is being done with an exponential. N integrate particular method is followed. Suppose n integrate, if you try to do with Simpson, no? Simpson method, Simpson rule or Euler method, no? Your integration limit is minus infinity plus infinity. And I'm sure that your error will be too much in integration. Therefore, alternate methods that have been adopted, that should be selected properly and that should be used. Otherwise, you'll have a problem. Problem in the sense that you have an error that is there in this function. This number will be too much of error will be there in this. You may not even get 1.6 itself. You end up with some other numbers. Because the limits are too big from minus to plus infinity. And that's going to be a problem. And not only that, if you have some functions of this type, you try to look at what is really happening. If I do this one before integration, I plot it. See what is the nature of the integrand itself first. Okay, x varying from somewhere about -5 to +5 and see what is happening. If this function is meaningful or not, or there's anything that's going to happen. What is dominant in this? Sin x by x feature is missing. We do not know where do they disappeared, and then see, this is not seen at all. Contributions. See, for example, this one. This I take to the 5 to +5, you see, or you can take it to 15 to -15. You are going -% remember. See, it's an oscillatory function with an exponential -5. Follow? It analyze the function. See, now we can find out the area under the curve. Can I integrate it? Find out that. Right? That gives an area under the curve, -+ and the consequence of exponential. Okay, what is that? What would be -x, and what would happen? Not only -x, but -x square. That's what the function is. Okay, equal -x square. Now I give a plot range on plot range. Try to have some knowledge about the nature of the function by plotting them. What happened to those oscillations? They are all disappear, or they're making contributions. That we have to think it over and then make sure that they're coming out with the contributions or not. No? So let me take this 3 to -3 to +3. So you can see now this effect cannot be seen. Taken over by this equal -x square. But its consequence should be there. Because this is e power -x square has a bell-shaped curve. In addition to this, there is an oscillatory component of sinc function. So that should also be reflected in your area. So that's why it become a complicated function here. And it has been defined as an error function. I know that what is this error of? Error. You know what is error? Okay. Quite interesting to look at the error function, how it is being defined. Error of z equal to 2 by square root of pi 0 to z e power -t square dt. This is what your error. So therefore, it is difficult to have a differential form back taking the results. Hello? This is what your error. And your limits is in 0 to infinity. 0 to z for any value, given value of z, the performance e power -t square into dt. That is what your error. So like that, you have to probe, understand more about the functions. Okay, right. Any questions? So people are able to follow the lectures. Fine. Lectures being followed, or it is simply listening and then just collecting information. Hello. You around, Sahini? Yes, sir. Sahini?
Hello, sir.
So we can close down now. Any clarity? What I'm asking is that people are able to follow things, or simply so you just find out.
Yes, sir. I contacted the MPhil students. They are all finding it very interesting.
Okay.
MSc students, they told me that they are working it out.
Okay.
In that way, it is they find it very interesting. MPhil